Hi, welcome back. We're going to talk about cluster analysis. This is chapter 14 from the Shmueli textbook. Cluster analysis is a method that allows us to group the individuals in our data set without any sort of prior information. And in some sense, you might say that it is listening to the data. And you want to be careful not to confuse this with clustering of variables. We are not doing that in cluster analysis, just the observation. The main idea in cluster analysis is to form groups or clusters of similar records by determining what those groups have in common. Usually we're going to do this for large data sets with lots of individuals and lots of observations. There are a lot of applications for cluster analysis. Some of them maybe you're familiar with. Periodic table of the elements is one that is done using cluster analysis. Classification of species, grouping of securities and portfolios. That's one that's done a lot in Wall Street. And among the others, the Army, if you've read the Lenoff and Berry text on cluster analysis, you'll know the Army uses cluster analysis to come up with uniform sizes. Let's look at another example, public utilities. And the goal is to find clusters of utilities that are similar to each other, where we have 22 different firms, and the 8 variables that we're interested are the ones that are listed here. In other words, we want to look at the characteristics of each of the firms based on these 8 different variables and see how they are similar to each other. So here's the data, and we've got the 22 different companies and the 8 different variables, and we want to know how they group together, and it's hard to do that just by looking at the data. And so if we use the cluster analysis algorithms, we can actually find out how these different utilities are grouped together, which ones are similar and which ones are not. And using cluster analysis, we're going to put these into groups without having to ask some sort of expert or someone with domain knowledge how they would do groups for things like this. And in a small data set like this, you might be able to get away with asking an expert who works in the energy business. But if you have a very large data set, then it becomes virtually impossible to group these things based on an expert's opinion. And that is where cluster analysis comes in. For example, if we were to look at sales on the x-axis and fuel costs on the y-axis, we could see that we have one group up here, high fuel cost, low sales. These things are all grouped similarly when it comes to fuel cost and sales. We've got another bigger group here, and then another group here, low fuel cost, high sales. So we could use cluster analysis to identify these things and say Idaho, Nevada, Texas, Puget, those are all similar to each other. New York, San Diego, United, New England, Boston, Hawaii, Pacific, those are similar to each other, and so forth. When we use just 2 variables, fuel cost and sales, it's very easy to see what's going on and see how these things cluster or don't cluster. But the question you should be asking yourselves is, what happens if we have more than 2 variables? Because humans are not very good at viewing things in more than 3 dimensions. Anyway, 3 we can kind of do, but once you get to 4, 5, and 6, then things start to get very difficult. So when we move on to multiple dimensions, we're going to need to come up with a distance measure. And then what are we going to do with that distance measure? So we're going to look at 2 different algorithms. One's called hierarchical, and the other one's called non-hierarchical. And they're both based on measuring the distance between points in whatever number of dimensions we're considering. So let's first start out by talking about hierarchical clustering. And there are 2 methods for this. One's called agglomerative, and the other is divisive. The agglomerative method starts with n different clusters, so each record is its own cluster, and then we join the records together into clusters until there's just one cluster at the end. And this is the most popular approach to cluster analysis. The divisive methods go the other direction. They start with one inclusive cluster where everything's in the same cluster, and then divide that into smaller clusters until eventually there are n clusters. So it's kind of going the backwards direction as the agglomerative method. First thing we need to do is measure the distance between records. We will also talk about measuring the distance between clusters in a little bit. The most popular distance to use is the Euclidean distance, and this just says take the distance between the first observation xi on the first variable 1 and the distance between that and xj on the variable 1. Square that and do the same thing for each of the i's and j's and the different variables. So here would be the second variable for the observation I and the second variable for the observation j. We're going to measure that distance. Like with some of the other things we've done already, the scale of the variables can highly influence the distance. And so one thing that we often are going to do is to normalize the data first, which means we're going to find the mean, subtract that from each of the observations, and divide by the standard deviation. In other words, we're going to calculate the z-score. For example, if we were to look at our utility data, we'd say the average sales is 8,914 with a standard deviation of 3,550. The normalized score then for Arizona's sales would be, this is 9,077. Those are the sales for Arizona. Subtract the mean, divide by the standard deviation, and we have 0.046. So that means Arizona is pretty close to the mean in terms of standard deviations. It's 0.046, but standard deviations above the mean. And you can see in JMP that when you do this, there is an option here to check mark, or you can check box the standardized data field, and that will do that automatically, so you don't have to go into the data set and normalize all the variables beforehand. Cluster analysis also works for categorical data. And to do this, we're going to measure similarity instead of distance, and there are several ways to do that. There's matching coefficient and Jaccard's coefficient. And there are several other distance measures that can be used. You can see that they're all based on statistical measurements. The other type of distance that we have to measure is what we call distance between clusters. And the simplest of these is what we call the minimum distance. And this is also called single linkage. And the idea here is if we have two different clusters, here's one cluster, we'll call that cluster A, and here's cluster B. Then the minimum distance is the distance, let's make it obvious, that is between the two closest members of each of those clusters. We also have what we call the maximum distance, or complete linkage, and that says if we have our two clusters, A and B, then we're going to take the maximum distance. But so this point here and this point here, whatever the maximum is, we would call that the complete linkage distance measure. We also have what we call the average distance, or average linkage, and this happens when we take the distance between all pairs in both of the clusters and then average those distances. And I'm not going to draw a picture of that because there's too many lines to do that. And then what we have is called the centroid distance, which is not to be confused with the average distance. The centroid distance said, let's find the middle point of each of the clusters. So here's cluster A. We would say, what's the average of all these points? We'll say it's like that. And then for B, the average of all those things is going to be here. So we just measure the distance between these center points. There's another method called Ward's method that is categorized as one of the agglomerative cluster analysis methods. And the idea here is to take into account the amount of information that is lost when observations are clustered together. In other words, when you put them in the same group, if they are much different from each other, then there's going to be a lot of information that is lost, and the error is going to be higher. So this is going to use what's called the error sum of squares to measure this distance, and that's going to be the basis as to whether to add more groups or keep smaller number of groups. And there is something called fast Ward method in JMP, which is an approximation to this and is automatically used for large data sets. I believe anything over 2,000 observations will automatically be used, will automatically have the fast Ward method used on it. So the way this works is first you start with n clusters, and so each record has its own cluster, and then you merge the two closest records into one cluster. And at each step, your two closest clusters are merged together, and this results in what we call a dendrogram, and this is what a dendrogram looks like. And this one happens to be displayed horizontally. Sometimes you see them vertically, but this distance here, from here going this direction on the x-axis, I guess we would call it here now, it measures the distance between each of the observations. So if we were to come up here and say New England and United, they're the first two in this agglomerative method. Whatever the distance is that we're using, these are the first two that get joined together. In other words, they're the closest to each other. So New England and United. So if you were to come over here and say, what's this distance? Whatever that distance is, that's going to tell us that those things are within that distance of each other, and not too far bigger than that. We'd see that Madison and Northern would be joined, and then we would go until the next pair are joined, and it's hard to tell. It's one of those three, just by looking at the dendrogram anyway, it's hard to tell. But you can see that we go from all of the records having individual clusters to there being one cluster over here, and we can say what's the distance at which that happens, and that means the distance between the records or the distance between the clusters, depending on which measure we're using. So the dendrograms are very useful because they tell us how many clusters we might have. If we were to draw a vertical line here, say right here, we would say we have 1, 2, 3, 4 different clusters, when the distance between the clusters is set to be whatever that number right there is. And notice that New York is all by itself, but Idaho, Puget, and Nevada grouped together, and then here we've got San Diego, Hawaii, Pacific, and so forth. And so you can see the different colors here correspond to a certain distance or a certain number of clusters. So let's see if we can find where this is. If we separate by this distance, and I guess that's marked here with that diamond, that tells us that at that distance we have 1, 2, 3, 4, 5, 6 clusters. Two of those clusters are singletons, and we'd be able to say that it looks like we've got fairly good separation between these. So that tells a good story that what's going on with this data. We've got 6 different clusters, and that could help us going forward. If we were to get new data, we could say how does the new data behave? Well, we can look and see which group it's most similar to, and that can lead us to making decisions about where to put it in a portfolio, where to, how to allocate resources to it, that sort of thing. So now we ask ourselves the question, how do we validate the clusters? Validation is a big part of what we do in data mining. So we want to ask whether the clusters we've observed are any good, or are they just artifacts of random chance? So the goal here is to get meaningful clusters, and sometimes just due to randomness we can get what appears to be clusters. So we want to actually look at the characteristics of the clusters and determine whether there is a good story that goes along with how these things are clustering, which will allow us then to come up with a label for the cluster. So we want to check whether there's stability, or rather that's a quality we would like to have. In other words, are the clusters stable? If I were to drop some of the observations out of the data set, would I still get the same clusters? And then I also want to see about the separation. What's the distance between the observations within a cluster versus the distance between the actual cluster? So what we would like to see is, for example, if we had a cluster that looks like this, that has very small within cluster variation, and if we had another cluster over here, also with very small within cluster variation, and then the distance between these things, however we measure that, to be large. So if we look at that ratio, then if we have a large distance between compared to the distance within, then we're going to have a better separation. And that's going to give us better clusters. So that's all we have for this video. Look for several others this week. We will continue by talking about k-means clustering, which is one of the non-hierarchical clustering techniques, and so we'll see you in the next videos. We'll also have a few examples, or at least one example from the textbook doing this using JMP. Okay, send me email if you have any questions.